Hello, Class 10. I know your board exams are right around the corner, so let's take a few minutes to do a really focused revision of one of the most important chapters out there, electricity. We're going to walk through all the key concepts together and make sure everything is absolutely crystal clear. Ready? Let's get right into it. So here's our plan for today. We'll start with the real basics. What is current and what are circuits? Then we'll look at the push that makes it all happen, potential difference. After that, the big one, Ohm's law. Then we'll see how to connect things in series and parallel. And finally, we'll wrap up with the heating effect and electric power. Just 5 key steps to really lock in this chapter. All right, first up, the absolute foundation of this whole chapter. We're talking about current and circuits. Let's get a really solid handle on what electric current actually is and what it needs to get moving. So, what is electric current? At its heart, it's really simple. It's just the rate that electric charge is flowing. Think of it like water flowing in a pipe. And just like that water needs a pipe to flow through, electric current needs a path. That path has to be continuous and closed, no breaks. And we call that path an electric circuit. And of course, there's a formula for it. This one is a must-know. Current, which we represent with the letter I, is equal to the net charge, Q, that flows, divided by the time, T, it takes to flow. So I equals Q over T. A super simple but really powerful little formula. So how do we actually measure current? Well, the SI unit is the ampere, and you'll see it written as a capital A. And what is 1 amp? It's just 1 coulomb of charge flowing past a point every single second. See how that connects right back to the formula we just saw? It's all linked together. Okay, so we've got charge, and we know it flows. But what makes it flow? Charges don't just decide to get up and move on their own. They need some kind of, a push, an electrical pressure. And that push is what we call potential difference. Now, the official definition is that potential difference is the amount of work you have to do to move a unit of charge from one point to another. I like to think of it like this. Imagine a water hose lying flat on the ground. The water's not going to go anywhere, right? But if you lift one end up, that difference in height creates a pressure that makes the water flow. Potential difference is basically the height for electricity. And yep, there's a formula for this too. Potential difference, represented by V, is the work done, W, divided by the charge, Q. V equals W over Q. This formula tells us exactly how much energy or work is being used to push each little bit of charge through the circuit. The unit we use for potential difference is the volt, written as V. And just like with the ampere, the definition is baked right into the formula. 1 volt is simply the potential difference you have when 1 joule of work moves 1 coulomb of charge. It's all beautifully connected. Okay, now we're getting to what is probably the most important rule in this entire chapter. We know about the flow, that's current, and we know about the push, that's potential difference. Well, Ohm's law is the amazing formula that connects the push, the flow, and the opposition that flow faces. So this is the formal statement of Ohm's law. I know it sounds a little wordy, but the idea behind it is actually pretty straightforward. It just means that if you increase the push, which is the potential difference V, then the flow, which is the current I, also increases in a predictable, proportional way. If you double the push, you get double the flow. The only catch is that the temperature has to stay the same. And here it is, the famous equation. V equals I times R. This is the heart of the chapter, right here. V is our potential difference, I is our current, and that new letter, R, that's resistance. It's the measure of how much a material fights against or resists the flow of charge. Now we can shuffle this formula around a bit. If we want to find the current, we get I equals V over R. And this shows us something really cool. Current is inversely proportional to resistance. That means for the same amount of push, if you double the resistance, you'll only get half the current. Makes sense, right? And the last version of the formula solves for R. Resistance is simply the ratio of the potential difference to the current. What's really important to remember is that resistance is a property of the material itself. It's what determines how much current is going to flow for any given push. So what actually determines a material's resistance? Well, it comes down to 4 key things. First, the length. A longer wire has more resistance. Second, its cross-sectional area. A thicker wire is like a wider pipe. It has less resistance. Third, the type of material it's made of. Copper has a very different resistance than, say, iron. And finally, temperature also plays a role. This formula right here wraps up those factors perfectly.
Resistance R equals rho times length L, all divided by area A. That funky Greek letter rho stands for resistivity. Think of it as a number that's unique to each material that tells you how much it naturally resists electricity. So, a long, skinny wire made of a highly resistive material is going to give you the most resistance overall.
So far, we've mostly talked about one resistor, but what happens when you have more than one in a circuit? Well, you can combine them in two main ways, either in series or in parallel, and how you connect them completely changes how the circuit behaves. This is a big one. Let's break these two down side by side because this is absolutely crucial for your exams. First, a series circuit. This is where you connect components one after another, end to end. The number one thing to remember is that the current has only one path, so the current is the same through every single component. The total resistance, you just add them up, R1 plus R2 plus R3. Easy. Now parallel circuits are different. Here, the current splits up and goes down different paths, or branches. For parallel, the most important rule is that the voltage across each branch is the same. The rule for total resistance is a little trickier. You have to add up their reciprocals. Really getting this difference is a game changer. So why should you care? Well, think about the wiring in your own house. It's all done in parallel. Why? Well, for one, this lets every appliance get the same voltage and pull whatever current it needs. And critically, if your lamp blows a fuse, your TV doesn't turn off. The rest of the circuit keeps working. And here's a weird but true fact. The more things you plug in parallel, the lower the total resistance of the circuit becomes. And for our last topic, let's talk about what happens to all that energy flowing through a circuit. A lot of times, it actually gets converted into heat. We're going to look at this heating effect and then learn how to calculate electric power, which is just the rate at which that energy is being used. This is Joule's law of heating, and it tells us exactly how much heat gets produced. The heat, H, is equal to the current squared, that's I squared, times the resistance, R, times the time, T. The really key part here is that the heat depends on the square of the current. So if you double the current, you're not going to get double the heat. You're going to get 4 times the heat. That's a huge difference. Now, electric power is just the rate at which energy is being used. For your exams, it's super helpful to have this little toolkit of 3 power formulas. The most basic one is power equals voltage times current, or P equals VI. But if you cleverly use Ohm's law, you can also get P equals I squared R and P equals V squared over R. Knowing which one to use for which problem can save you a ton of time. Now, the official SI unit for energy is the joule, but a joule is actually a tiny amount of energy. So for commercial stuff, like your electricity bill, we use a much bigger unit, the kilowatt hour, or kWh. That's the unit that you get charged for. 1 kilowatt hour is just the energy that a 1,000 watt device would use if it ran for a full hour. And for perspective, that's equal to 3.6 billion joules. And let's finish up with one last thought. Just look around the room you're in right now. The lights, maybe a fan, anything plugged into the wall. Based on what we just went over, you know for a fact whether that wiring is in series or in parallel. But can you explain why? Applying these ideas to the world around you is the absolute best way to make them stick. And that's our full revision. Go over these key points, do some practice problems, and you are going to be in great shape. All the very best for your exams.